Okay, so we're going to continue with what we were doing yesterday, looking at rates of change, and look at 3 different problems before we move on to the next section. First one we're going to look at is marginal cost. And marginal cost is approximated by the derivative of cost. Technically, marginal cost is the change in cost per 1 unit change in production. And if you think about manufacturing, for example, most manufacturers produce thousands and thousands of things per day. And so a change of 1 out of thousands, that's a very small change. And in calculus, right, with the derivative, we have these very small changes that we look at to try and predict the overall change at that point in time. So marginal cost is actually like if we have a cost function, it's x plus 1. Right, so we look at the cost at a particular place and we add 1 more unit to that, and we compare that to the cost of not producing an extra unit. Right, so that is change in y for 1 change in x. Right, the denominator of my slope, and basically I'm just finding slope here, would be x plus 1 minus x, right, which is just 1. Which is just the change in cost with 1 extra unit minus the change in cost at whatever point we pick. So this is the technical definition right there of marginal cost. Now, sometimes that cost function is pretty complicated. Derivative functions tend to be slightly less complicated. And so what we can do is we can approximate that. And if you think about our point slope form we've been playing with, right, y minus y1 equals m times x minus x1. Hopefully you've learned or noticed that that right there comes from the slope formula. M equals y2 minus y1 over x2 minus x1. So I'm just going to do a little funky algebra here to make a relationship. If I want to get this denominator out of here, the x2 minus x1, I would multiply it to the other side. So that would give me m times x2 minus x1 equals y2 minus y1. And you should notice here that this right here is essentially that with things on opposite sides and named a little bit differently, right? So y2 minus y1, here I have y minus y1. Here I have m times x minus x1, here's x2 minus x1. So the point slope formula is just a variation of the slope formula that's very useful for finding lines quickly if we know a point and the slope. So what we have right here is the marginal cost definition, and my claim is that it's approximately equal to the derivative of cost. So our m, when we've been playing right here, that's our derivative. So switch colors, let's go to green again. So the y minus y1, that's the same thing as this c of x plus 1, that's my y. y1 is going to be c of x. Right, so there's the difference in my 2 y values. M, well, that's my derivative. My derivative here would just be c prime of x. So that's how I find the slope. And x minus x1, well, that's just 1. And if I multiply 1 by that, nothing happens. So this, based on the point slope formula, which is based on slope, is the relationship that marginal cost and the derivative of cost are approximately the same. Now here I wrote they're equal at first, but I just want to show that they're approximate by looking at a quick sketch of a graph. So they're not exactly equal, they're just approximate. And they're pretty darn close, as we'll see in the next example. So if I were to graph roughly, let's say this is my cost function there, and I pick some point on that right there, and then I graph the tangent line, which think about there might be the tangent line. And then here is my x value right here, x. And then I scoot over. Now, usually we scoot over h, but here we're just going to call that 1. So x plus 1. Oops. Switch back to pen. So that distance right there, usually we call h. We're just letting h equal 1 for marginal cost. And we trace that back up. So I have this other point on the curve. And it's this slope right here, 1. And then this right here is going to be my c of x, y value. So that's my y1. And then this y right here, that would be the next one. That's like my y2 right there. And so this change right here, a lot of times I call that delta y. That's our marginal cost. Now, I also found the tangent line, and this tangent line right here has a slope, m, that comes from the derivative where we plug in this x value right there. And when we extend that out 1 unit, what we end up with is, and just think about this for a sec, we have our y minus y1 equals m times x minus x1. And the difference in my y values, I already mentioned, well, that's this right here. And then as far as the change in x down here, this is my x minus x1. That's just 1, and my m is the slope. So, and now I'm saying that's approximately c prime of x, right? C prime of x is the slope. If I view that as c prime of x over 1, then that makes this rise right here, that rise right there, that is my c prime of x. And notice in this case, c prime of x is a little bigger than the marginal cost. But given that we're kind of zoomed in here and talking about thousands of units of x, so x is in the thousands probably, millions maybe, a change of 1 is a pretty small change compared to thousands or millions of things. So the change in the function, that's like the secant slope here, is a little different than the tangent slope in general. The closer you zoom in, the closer those two get to each other, right? Can you see that? The height here is almost the same as the height there. And the closer we get to that point, the closer they are together. And that's the idea of the instantaneous rate of change. Here, we're not quite doing instantaneous because we're letting the change be 1. So let's look at an actual function and apply this. And we'll find both the marginal cost and the derivative, the change in cost based on the derivative, and see how close they are. So let's suppose our cost function is 0.001 x squared plus 7x plus 5,000. All right, so we have a fixed cost here and we have a variable cost there, is the way to think about that. And we're going to look at x equals 1,000 units of production. So maybe we make baseball hats or we make cell phones. So we're making 1,000 units. What if we bump production by 1 more unit? Is our cost going to change dramatically or not? So the marginal cost, which is abbreviated MC, is just, again, cost at x plus 1 minus the cost at x. So for us, that would be the cost of 1,001 units versus the cost of 1,000 units. And what I want to do is compare that, see what that is, and compare that to the rate of change at 1,000, which is the tangent slope. So we're comparing basically here the secant to the tangent, see how different they are. So in a sec, we'll plug this into a calculator, but let's find the derivative function of cost here. And so that would be 2 times 1,000, which would be 2 thousandths, 2 thousandths plus 7. So we'll just take a look at each of these. So whip out a calculator and let's see what these guys are like. So I'm going to use GeoGebra, it does most weeks great, or a TI or a Casio. So I have my cost function, and that is equal to 1,000th squared plus 7x plus 5,000. And I want to see that, but I'm going to type my marginal cost in 2. I'm going to call that M for margin, and that is 2,000ths x plus 7. And I need to change my scale here. So let's see, similar to Desmos, I can go into the settings, and I want the x value to go well past 1,000. So I'm going to go out to 2,000. And then I guess I need a guess at a y value here. I'm going to guess at 100,000. Okay, so that was a little too high. Calculate what is C of 1,000, and it is 13,000. So maybe I'll go up to 20,000. All right. So here's my cost function. I'm concerned about x equals 1,000, so that's right there. And the marginal cost could be found by taking C of 1,001 minus C of 1,000. So I get a marginal cost of 9. So I'll write that down in a sec, 9.001. If I take the derivative at that point, which is M, plug in 1,000, I should get a pretty similar number. So notice that they're very close together. So they're, in terms of dollars, they're about the same. So back here. So this one right here is about 9.001. And what are the units there? Well, cost is typically going to be in dollars. And these are whatever units I'm selling. And let's suppose they're hats, just for fun. I got a new hat yesterday. So this would be dollars. Oops, I missed a 1 there. It's supposed to be a 1. No, it was one place over, wasn't it? Nope, that's where it was. Okay. Dollars per hat. And same thing here. We took the derivative of cost with respect to x. Cost is dollars, x is hats. So again, when I plug in 1,000 here, I get $9 per hat. And they're pretty darn close together. And that's going to be true for the most part. So what this is telling me is the cost will increase by $9 per hat if I increase production if we're already at 1,000. So let's write a sentence explaining what that means. So if we are producing 1,000 hats, maybe it's per day, then an increase in production one hat means cost increases by $9 per hat, right? It's not an increase of just $9, it's $9 per hat. How many hats are we making? We're making 1,000 hats, maybe 1,001 hats. We just increased production by $9,000 by deciding to make one more hat than we were already making. So this is a bad point to increase production at because the cost is increasing too much. Now, the decision shouldn't be made on cost alone. We should also be looking at revenue and profit. So this is just one part of that picture. Point here is application of derivative in business. They're called margins, and a margin is really just a derivative, and it's an application of rate of change. Pretty cool one. All right, moving on. Let's look at gravity, my favorite subject. When I decided to study math, they said you got to take science, and we recommend physics, and that was the first time I took physics, and I loved it. Did not take physics in high school, just chemistry, really. So gravity pulls stuff down, right? And if we're going to measure here in meters and seconds, And so acceleration due to gravity in meters per second is negative 9.8 meters per second, which a lot of physics people like to write as negative 9.8 meters per second squared. I think I told you before, squared seconds freaks me out, but I'm sure Doctor Who has an explanation for that. All right, so then let's see, we're gonna look at a position of, we just drop an object. So let's drop a ball from 20 meters in height. So a little over 60 feet up in the air. So like we're on a short 3-story building or a tall 2-story building. No, you get that right? That'd probably be like a 4 or 5-story building, wouldn't it? Yeah. All right. So, and what I want to look at here is I want to look at the speed when it hits the ground. And I want to look at its average velocity over the fall. Let's call it average speed over fall. So the speed when it hits the ground, that's the instantaneous velocity, right? Bang, it hits the ground, that's an instant. Whereas average, that's secant, right? That's not instant. So for this one right here, I need to calculate what is the velocity function. And for this one right here, I'm just looking at the change in velocity, the average speed over that time. So that would be like v of t2 minus v of t1 divided by, oh no, shit, that's change in, sorry, I lied. The average acceleration. That would be s of t2 minus s of t1, change in position over change in time, t2 minus t1. Got a little carried away there. So let's see, first we need a position function. So the position function here ends up being s of t is equal to 20 minus 4.9 t squared. And we'll see how that 4.9 relates to the 9.8 in just a second here. Velocity function, based on that, just is the derivative. Let's change color, please. So if we look at the derivative of position over time, that is our velocity function. And so that would be the derivative of 20 is 0. The derivative of t squared is 2t. So I'm going to get negative 9.8 t. And so acceleration is the slope, the rate of change of velocity, right? And we looked at that before. dv dt is a of t, and a of t is constant. So I had that up there. So if we were to take one more derivative here, right, we would see that a of t is just negative 9.8. So position, velocity, acceleration there. So for part A, I want the instantaneous rate of change when it hits the ground, but, oh, I don't know when it hits the ground. I guess I better figure that out next. So we've got position, s of t is equal to 20 minus 4.9 t squared. We want to know when it hits the ground. Ground level is going to be 0 usually. So we would subtract the 20 to the other side, divide by 4.9. Negative over negative is a positive, and then take the square root. And normally we get plus or minus the square root, but we're talking about time here, and we're not going to go backward in time because nothing was happening before I dropped the ball of any significance. It's only after, so I want the positive one. So that's the time. We can approximate it, but when we do the calculation, we're going to use the exact value. So let's get a new GeoGebra screen for this one. I want the square root of, and there is a calculator button here that you can choose if you're not familiar with GeoGebra. I want the square root of 20 over 4.9. It's about 2.02-ish seconds. So rough sketch. Here's 1 second, here's 2 seconds later, it's going to hit the ground, probably a little closer there. And then here's 10 meters, here's 20 meters. Oops, that's a little high compared to 10. All right, so this thing starts here and parabolically heads down to there. Not the best sketch, but we'll go with it. S versus T. And I want to know the instantaneous velocity when it hits the ground. And so that would be V of the square root of 20 over 4.9. And beware of plugging in approximated answers, and then so rounding once, then rounding again could throw your answer too far off the system. So my velocity function is just negative 9.8 times that square root 20 over 4.9. And so I'm getting negative 19.8 if I went to 1 decimal place. That's even a 2 decimal places, 80. So this is negative 9.8 times the square root of 20 over 4.9, which is approximately negative 19.8 units here, 80 to 2 decimal places would be meters per second. Now to get the instantaneous, the average velocity from start to finish over the fall here, that would be find V of T2, S of T2, which is the square root of 20 over 4.9 minus S of 0 divided by the time difference, 20 square root of 20 over 4.9 minus, we started at time 0. So let's try that in a calculator. So I'm going to get my function, so I don't have to retype it repeatedly. S of x equals 20 minus 4.9 x squared is my formula. And here, GeoGebra nicely says, hey, that's about 2.02. Thank you. And then I want a fraction with S of that square root. And minus S of 0, which I can clearly see as 20, but I might as well plug in the function notation, over the change in time, which we just calculated to be the square root of 20 over 4.9. Let's see, did I type that correctly? Yeah, looks like I typed it correctly. And if you look at that, since this was a small span in time, we don't deviate too much from what gravity is doing there. So let's see, yeah, that looks like a calculator, right? So it looks like it's about negative 9.899. And again, let's talk about why those are different. Oops, get 2 decimal places, negative 9.90. So this average one, that covers everything, right, from here to here, but really I'm only focusing on this point and this point. I'm kind of ignoring what happens in the middle. So that's this one right here. This one right here is only focusing on that instant when it hits the ground there, right? So the slope at that instant, the rate of change at that instant. And so we're definitely going to get different results from that. Notice that the instantaneous velocity is about double. And if you think about that, right, that's our slope at that instant. Slope is usually rise over run. So that is a per unit change, right? 1 in the bottom per unit. Unit literally means one, right? So that's kind of like at that instant, kind of divided by one, whereas over here, we're looking at a span of about 2 seconds. Okay, so notice the half that's kind of going on in there is kind of related to that right there. So instantaneous velocity versus average velocity. If we looked at the average velocity from 1 to 2, that would definitely be different because it's moving slower up here than it is over here, right? Think about the tangent slope there versus the tangent slope there. So every average velocity we find, if we change that span of time, we're going to get much different results there. So if we went from 1 to 2, we'd find a number much closer to that. And as we let that other x value get closer and closer to 2, we'd find the average is getting closer to the instantaneous. So that's just secant versus tangent slope. Okay, next problem, population. So we had a homework problem similar to this, and hopefully it went okay. And we did a problem like this a while ago. Let's look at population of bacteria. And let's suppose we've been studying this and we've measured the population, and we found a pattern to the population that is 5t squared plus 20t plus 200. And we want to know what's the rate of change of the population at 3 hours. So rate of change, right, that's the change in population over change in time, which we can use the derivative to calculate that, given only one time. And so we need to find p prime of t. So that would be 10t plus 20. And then if we evaluate p prime of t at 3, that gives us the rate of change we desire. So 10 times 3 plus 20 is 30 plus 20, or 50. And again, what are the units here? Well, we have a change in population, so that's bacteria, over a change in time. Ooh, what was the time here? Oh, hours. Bacteria per hour. So what this tells me here is 3 hours into the growth of the bacteria, the population is increasing by 50 bacteria per hour. So 3 hours into bacteria colony growth, population is, now I don't want to just say change because that's a positive number, so I would say increasing by 50 bacteria per hour. And just something I want to be clear about, homework is practice for the stuff that we're reading in the book and we're learning in the class lectures. On the written test, right, you got to show me some work. So here's some work. And anytime we have an application, I'm going to ask you to tell me what it means. And so you do want to think about what these applications mean. Like, what does this change in cost tell us? What does this change in bacteria tell us? So anytime you have a situational problem, think about what does the number we calculated mean? And I'll try to emphasize that with a sentence when we do this. All right, so I think those are the main things you might have a problem on. Were there any homework questions aside from what I covered here that you got stuck on if you played with it yesterday or last night? Otherwise, you get to play some more tonight. Okay, what's up on 3.3?